Welcome to Chandrashekher Research Academy of Business Studies. In today's video, we're diving into the fascinating world of probability distributions. Probability distributions are essential tools in statistics, helping us model random events and make informed predictions. They form the backbone of decision-making in fields like business, finance, and data science. In this session, we'll cover the key aspects of probability distributions, including their types, salient features, and practical applications. Whether you're a student, a researcher, or a professional, this video will provide you with a clear understanding of how distributions work and how to apply them. Let's get started. Let's begin with the basics. A probability distribution is a mathematical function that describes the likelihood of different outcomes in a random experiment. There are two main types of probability distributions: discrete probability distributions. These deal with outcomes that are countable, like the number of defective items in a batch or the number of heads in a coin toss. Continuous probability distributions. These deal with outcomes that can take any value within a range, like the height of individuals in a population or daily stock market returns. Understanding probability distributions allows us to summarize complex data, visualize patterns, and model uncertainty effectively. Now, let's explore the salient features of discrete probability distributions. Finite outcomes. Discrete distributions focus on a finite or countable set of possible outcomes. For example, the number of times a dice roll shows a 6. Probability mass function, PMF. The PMF assigns a probability to each possible outcome. The sum of all probabilities equals 1. Key distributions. Examples include binomial distribution, used when there are two possible outcomes, like success or failure. Poisson distribution, useful for modeling the number of events occurring in a fixed interval of time or space, like the arrival rate of customers. Application. Discrete distributions are commonly used in quality control, operations, and customer behavior analysis. For example, consider the binomial distribution. If a factory produces items with a 90% success rate, we can use this distribution to predict how many items out of a batch of 10 will meet quality standards. Discrete distributions are all about counting possibilities and assigning probabilities to each one. Next, we move to continuous probability distributions, which have their own unique features. Infinite outcomes. Unlike discrete distributions, continuous distributions deal with uncountable outcomes, like measurements of time, weight, or temperature. Probability density function, PDF. The PDF represents the likelihood of a value falling within a particular range. Unlike the PMF, the probability for an exact value is 0. Instead, we calculate probabilities over intervals. Key distributions. Examples include normal distribution, the most widely used, often referred to as the bell curve. It models many natural phenomena like test scores and stock returns. Exponential distribution, used for modeling time between events, like the time until the next customer arrives. Application. Continuous distributions are vital in areas like risk analysis, finance, and operations management. For example, consider the normal distribution. If the average height of individuals in a region is 170 cm with a standard deviation of 10 cm, the normal distribution helps us calculate probabilities for a range of heights, like the likelihood of someone being between 160 and 180 cm tall. Continuous distributions give us powerful tools to model and predict real-world scenarios where values vary within ranges. Now that we've explored the differences between discrete and continuous distributions, let's summarize their applications and see how they fit into real-world decision-making scenarios. Now, let's dive into three key concepts that lie at the heart of probability distributions: mean, variance, and standard deviation. These statistical measures help us summarize and interpret data effectively. The mean is often referred to as the average. It represents the central value of a dataset or distribution. To calculate the mean, you sum up all the values in the dataset and divide by the number of values. The mean provides a single value that summarizes the entire dataset, giving us a sense of where the data is centered. Next is variance, which measures how much the data points deviate from the mean. A larger variance indicates that the data is more spread out, while a smaller variance suggests the data is closer to the mean. To calculate variance, subtract the mean from each data point to find the deviations, square each deviation to avoid negatives, and find the average of these squared deviations. The variance of a data set tells us how much the data points differ from the mean. Finally, we have standard deviation, which is the square root of the variance. It brings the measure of variability back to the same units as the original data, making it easier to interpret. Standard deviation provides a more intuitive understanding of variability compared to variance. For example, if you're analyzing stock returns, standard deviation gives you a sense of how much the returns fluctuate, helping you assess risk. To summarize, the mean tells you the center of the data. The variance measures how spread out the data is. The standard deviation makes this spread easy to interpret in real-world terms. Together, these metrics provide a complete picture of the distribution, helping us understand both the central tendency and variability of the data. Whether you're a student or a professional, mastering